I accidentally closed the window with the tablet, so I have to figure out how to reopen closed window. Hopefully it doesn't, like, drop the stream. I guess we'll see. No, it's still going. I could close this window, apparently. But my chat might be broken, so hold on. I gotta do that, and then I gotta pop out the chat again. You get to see behind the scenes here. Did it capture the right window? It did, okay. There you go. I mean, we were supposed to start anyway. I just didn't mean to tap the corner of my pad, which interpreted that as a click, and I guess clicked the X. I gotta move this over here. I don't need Discord open, so that can get minimized. Okay, there we go. So now we're actually on track. Welcome to lecture today. It's Thursday, week 4. Just some quick announcements. Lab worksheet number 2 is due tonight. Please make sure you upload a .xlsx file by the deadline. Again, it will not accept other file types, so you need to make sure you click on the correct thing. That has caused me no amount of grief from trying to contact a few students like, I haven't gotten the file from you, please send it. And hopefully you did that today. I haven't actually had time to check my email yet, but that will be done. I'll do that during the break or afterward or whatever. Secondly, quiz number 2 is due Monday. I know there was a concern about, wait, was it supposed to be due last night? So no, that was a typo. I used the same slide for Chem 121, and I had their announcements. So if you came in early yesterday and saw, oh crap, quiz 2 is due tonight, that's not the case. It's actually due Monday, and it says that on Canvas. That's where I get these numbers from to post them on the announcements. But I do make mistakes, and I apologize for that. I will look at everybody's quiz 1s tonight. I was going to try and do it last night, but the labs just took so long. I finished grading them at like midnight, and I was like, nope, that's it. I can't do it anymore. The lab number 1s have been uploaded to you. I believe what you do is you click on your assignments tab, and then you click on lab worksheet number 1 in that assignments tab, and it should have a little comment from me that says, hey, this is the worksheet that I gave you. And then you can either upload that to Google Sheets, or you can just open it in Excel. I wish we could do fission. Fission's 163. Quantum mechanics is sort of the start to get there. You do need to know quantum mechanics to understand fission. I mean, just a little bit. They are slightly related. But before we do that, we have to do the rest of Chapter 6, which I kept calling Chapter 5 in my head today. I don't know why. So I think this is the slide that we left on. I'm going to leave those examples for you. We're going to talk about mass percentage today. This is a way to express concentration in ways that aren't molarity. And you've actually seen one of these ways already. This was in the soda experiment for lab number 1, where I gave you a mass volume percentage of soda. And so there's all different ways to express concentration, and we're going to use them all for various applications, depending on like what the solute is and what the solution is and that sort of thing. What's important is that we indicate what these units are so that people know. If I tell you it's 7% sugar, that being mass percent versus mass volume percent leads to a very different outcome. And so the way that we're primarily going to do that is to do something like this. So whenever you see mass percentage, you're going to see something like this, or that. MM is mass over mass. W over W is weight. And so what that means is you're not putting volumes in here. So very common way to express mass percentage is you'll see a percent number, and it'll have that abbreviation after it. The formula is right here. Mass percent is mass of whatever component you're looking at divided by mass of solution times 100%. This should look just like the mass percent formula that we were using before. And the reason for that is it is exactly the same percentage that we were using. In general, you're going to be using the solute to figure out the percent composition, but if there are a bunch of solutes, you can actually determine them independently. But otherwise, this formula is used pretty much just like you would expect. If I sell you a bottle of bleach, for example, and I say that it has 7.4% sodium hypochlorite, that's what that OCl is hypochlorite. That means that if I were to weigh out 100 grams of bleach on a balance, in that 100 grams, 7.4 of them would be NaOCl. Now, that's not super convenient because liquids aren't easy to weigh. Like, you have to put it in a container, you have to tear the container before you do that, and so on and so forth. So we have another way of measuring percentage, and that's mass volume. And I think that that's on the next slide after this example, yeah. All right, so here's an easy example, and then we'll do a harder example. What is the mass percent of HCl in a sample of 0.150 molar HCl solution? Here's the density. And so now, you're probably looking at this and saying, okay, I know the formula, but I got a bunch of different parts, and I don't know what to do with them. In fact, I think a student emailed me about this question, or a similar question much earlier. When you're working with units of mass percentage or concentration and molarity, one of the things that we often give you is the density. And there's a reason for this. So let's highlight the density here. I don't know why I got that is in there, but that's okay. I missed the problem, so hold on. Ah! It tries to stick my window to the edges, and I don't ever expect it. I'm not on Photoshop, though. There we go. Oh, I don't see the boundary of my box. Alright, am I on the right layer? Let me check that real quick. Yeah, okay. So, I can't see the problem because the Photoshop panels are in front of it. There we go. So what we know about this is that I know that this is the molarity, which is the same as me writing this, which is also the same as me writing this. And that should give you a clue as to how you're going to use the density here. Because we know that the density of this solution is this. There's this many grams of HCl per milliliter. So that's the density. So how do I get mass percentage out of this? So to figure out mass percentage, we'll write down the formula. So that would be the mass of HCl over the mass of the solution times 100%. So how do I put all this information together? Well, I need the mass of HCl, first of all. How would I get the mass of HCl out of here? Well, what I would do is I would take the molarity and times it by the volume if I knew what the volume was. How would I get the mass of the solution? Well, I would take the density and multiply by the volume if I knew what the volume was. There's an interesting commonality we have in here. What is the volume? Well, it doesn't say in the problem, does it? But do any of these properties change with volume? If I have 10 liters of 0.150 molar HCl, or if I have 1 liter of 0.150 molar HCl, they're both 0.150 molar HCl solutions, and they both have the same density. So you get to pick whatever volume you want for these types of problems, because it doesn't matter. Molarity and density at a given amount, so like if I have HCl solution at this concentration, and that concentration is the same no matter what volume I have, then the density will also be the same. So let's do this. We're going to come down a little bit. We're going to say, I'm going to assume that I have 1 liter of the solution. Because if I have 1 liter of the solution, then what I can do is I can say, okay, I have 1 liter, And I can times that by the density. If I turn that into milliliters. Now, something important that I just realized that I wrote up here. I'm going to add this in red. When we refer to the density of the solution, what's in the solution? It's not just HCl, because it's not solid HCl in like a cube that we're measuring the density of. It also includes the water. And so I forgot to write down the solution up here. I was thinking it in my head, but I didn't actually write the word solution right here. And I'm going to write that down here because we're also using the density. Because when I am done with this calculation and I hit enter, what's going to come out is not going to be the mass of HCl. It's going to be the mass of the solution, which is this part of the equation right here. So let's plug in all these numbers. This is 10 to the minus 3. And then I forgot the density. What is it? 1.19 grams of solution per milliliter. And I don't know where I put my calculator. There it is. And so the number that my calculator spit out was 1190 grams of HCl solution. So that's the mass of the solution. Now we just have to find the mass of HCl. And then we're all set. So, again, remember that if we assume that we have 1 liter, I can use the molarity to figure out how many moles we have. So I know how many moles of HCl there are per liter. And this one is just the HCl. Because in molarity, it's moles of solute divided by liters of solution. So the solute is taken care of right here. And then finally, you could say, oh, well, if I know how many moles of something I have, I know how many grams of it I have. And that's going to give us our mass of HCl. So let's run the numbers. First, let me cancel out my units. So the molarity of my solution is 0.150 moles HCl per liter. And I don't know what HCl is per mole. It's like 36.45. 36.46, okay. So I got this as my answer. So the mass of HCl in the solution is 5.47 grams. All the rest of it's water. So now that we have that information, we can find a mass percentage. And so I could say mass percent is the mass of the component, which is the HCl, and the mass of the solution, which is 1190, times 100%. The units cancel out. I punch it in my calculator. And I get 0.460. So I'm going to identify what the solution is, and then I'm also going to do this. And the reason I want to do that is because I don't want somebody to look at that and interpret it differently. And think, oh, that must be a different concentration than what it actually is. So that's how we would compute that sort of problem, using the molarity and the density. Do we assume 1 liter of solution every time? I like to pick 1 liter because it's a nice round number, and you can say exactly 1 liter. So that way you don't ever run into sig fig issues with the number you choose. However, you may choose any number that you want because it's all proportional. So if I instead picked like 1.5 liters, then the number that I would have gotten right here would be 1.5 times larger. And the number that I would have gotten here would also be 1.5 times larger, because the number that's changing is the first number. MM stands for mass percent, so mass over mass. W over W is weight over weight, and it's commonly you see the W in the medical profession. It's just that you'll see both abbreviations. M is probably the more correct one because we prefer to use mass instead of weight, because what we are measuring here are masses and not weights. But yeah. That's right. So if you have 1 here, I lost my cursor. There it is. If you have 1 right here and 1 right here, 1 divided by 1 is 1. But if you have 2, for example, you use 2 liters instead, you'll get double this answer and double that answer. Or you could just say this 2 would cancel out with this 2. Because mass percent's a ratio. It's always going to be the same percent, regardless of what volume you're using. All right, let's do another one. This time we're going to look at volume percentage, but it operates exactly the same way because we're just using volumes instead. So here's the formula for that. Volume of component divided by volume of solution times 100%. What were the formulas used to get mass percent? That was on this slide right here. And so you can see that this formula is exactly the same as the volume formula that we have on this slide. Oops. All right. Now, I believe I have shown everybody the volumes don't add up video. Is that right? Did we see volumes don't add? I don't remember which class is which when I get to this part of the content. Okay, so we have seen it. Okay. So here's that link to that, but we already saw that in a previous video. I think I was just talking about it with molarity or something. Could we achieve that answer by manipulating another formula? I'm going to go with no, just because we're trying to get mass percentage, so you need to actually divide and use the mass percent formula to get that answer. I mean, there may be other ways to manipulate the numbers to get them into a form to put into that formula. But in order to do the problem, you do need the mass percent formula. That being said, a lot of mathematics is just, hey, did the units work? If it did, you get the right answer. So if you find a unique method, it could very well work, but I guarantee it will take longer. The ways that we're showing you to solve these problems are, strategically speaking, the fastest. These are the ways that are accepted and done by professionals in engineering and chemistry and biology and whatever. Now, as I mentioned on this slide and we saw in the other video, when you add volumes together, they don't sum to what you'd be expecting. So if I give you two different substances and I add them together, I have to tell you what their sum is. And if I don't, then you can't solve the problem. It's impossible. Now, if you add 2 solutions that are the same solvent, for example, like 2 benzene solutions, I have benzene A and benzene B, and I mix them together, then they do sum together, even if there's like salt in one of them or the other, even though salt isn't soluble in benzene. That was the example I thought of. Yeah, a question in the chat there, yeah. So if you had aqueous solutions and you put them in the same container, they should add up to be the same. Excuse me. Now, there will be some slight amount of error with that because you're adding 2 different solutes, and those will fit into different orientations and fill in each other's gaps. But being technical about the molarity of those components versus the molarity of water, water is by far the most abundant substance in the solution. And so the volume will change very negligibly if both of your things are water. So like if I had an NaCl solution and then a KBr solution and I put 50 and 50, I will get extremely close to 100. Probably so close that you wouldn't notice the difference. But technically speaking, this is true for virtually every situation. And again, I have to give you the volume of the solution in order for that to be a solvable problem. And so in the next problem, I am going to give you that. So let's look at this example. If a specific brand of nail polish is 60% acetone and the rest is water, how much acetone in grams is in the nail polish remover if the bottle has 500 milliliters? And here's the density. So using this information and the formula that I just showed you on the screen, what I want you to do, I want you to try this for just a second, because I apparently need to chug more water. My throat's really scratchy. I'll just leave it on the screen like this. But give it a shot. Try and work with the numbers for just a bit, and we'll be back in just a moment to go over the answer. So it looks like people are starting to get the answer. And despite chugging water, I still have phlegm in my throat because I am gross, I guess. I don't know. I'm not sick or anything. At least I hope not. I did just go to the store, so dun 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 dun. Let's see here. All right, so we know that volume percent, I'm in the wrong color here. Volume percent is the volume of the solvent, or a solute, sorry, divided by the volume of the solution times 100%. Now, I need to know the volume of the solute, which is the acetone, in order to solve the problem. But fortunately, I already know the number. It's 60% acetone by volume, and the rest is water, whatever volume that is. So that would mean that if I had a liter of it, so if I had 1 liter of solution, then I could say, okay, well, if I know the liters of the solution and the liters of solute, that would tell me how many liters of solute I had, which is acetone. And I have that ratio right here. It's 60%, right? If something is 60%, that means that I have this much per 100. And now that I know that... oh, how many sig figs did my number have? It actually had 3, so I gotta sneak a 0 in there. Now that I know this, I can then use the density to figure out what the mass of this is. And so this is probably what you did. I don't know what the density is, 0.784. 0.6 times 0.784 over 1 times 10 to the minus 3. That's not the number that you guys got. That's interesting. What happened? Oh, I used a liter. I don't know why I did that. Okay. So, yeah, that's the issue. So all my units worked out, and I was like, wait a second, I got the right answer. Here's where I have a mistake here. So I'm going to take this 1. That's what the problem's actually asking you, right? So how much acetone is in 500 milliliters? I don't know why I just immediately wrote down 1 liter. That's because I wasn't reading the problem. So now this number becomes that. And now I bet I'm going to get the answer that you got, because I got an answer that's like twice as big as it seemed like it should be. Yeah, 235 is what I got. That's the wrong unit, though. Hold on. I'm on auto today. Like, I'm just not thinking about what my answer should be. There you go. So to solve this problem, I used the volume percentage, which we knew was 60% from the problem, which I put right here. To figure out what component was acetone, and then I was able to find the grams of acetone using the density. Once, I started with the correct volume. That's okay, mistakes happen. Alright. Here's the last type of... Oh, question, let's see here. When you multiply by 100%, is that 100 or 0.1? So you want to multiply by the number 100 and then put the percent on it like it's a unit. So this is actually a number with a unit attached to it. Because percent is out of 100. If you have it as a decimal, then it's out of 1 instead, and not actually 0.1. Sometimes it's useful to express things as decimals. Sometimes it's just useful to express them as numbers. So in the previous slide, when I said it was 60% acetone, I could have done this instead. But I wrote it like this. And those are both equivalent. Because this 0 would cancel out, and then the decimal would move over 1 for each of them. I could teach algebra, I guess. Algebra seems pretty straightforward. This is the last one. I think the only reason that we really use this formula is because this is just the medical standard to make saline solution. That said, we did use it in the laboratory for the drink lab, where I asked you to figure out the mass volume percentage of sugar solutions and soda. So it might be more common than I think, but by far, this is the most common use for this that I'm aware of. This is how you make saline solution for IV. You put 0.9 grams of saline of sodium chloride into a liter of, or enough water to make a liter of solution. Component and solute are the same thing, yes. I'm just not writing the word solute because you might be mixing two things together in like equal proportions, and you would get 50%. Generally speaking, we are not going to be working with solutions that are like 90% HCl or something like that, where the solvent would then be the HCl by definition. So it's just a more technical way to write it. But component can be whatever you want it to be, really. Now, in this expression, you're going to notice that the units don't really cancel, because you're going to get something that looks like a density. And this is sort of just an obnoxious side effect of, hey, this is a unit that we use. Because when you do this sort of problem, and you get your answer, this is the only unit that's left. And what happens to these units that are left here? Well, what they do is they do this. Boop, boop, boop. I don't know where they go. They're just gone. They fade away. Which to me is really obnoxious as a scientist. I'm sure that there is some definition out there where it's like, oh, well, we divide by the activity, which is in grams per milliliter. And so that cancels the units out. And so you divide by the number 1 gram per milliliter or something like that. For our purposes, instead of like learning that proof and worrying about that, we're just going to say the units just cancel some mysterious way. And so when you do this problem with mass volume percentage, the end output should always just be a percent. Just like before, there is abbreviation. There is an abbreviation for this, and that abbreviation is MV. You may also see WV. They're both the same. Whoa. I was trying to wipe something off the board because it had like a speck on it, and my pen hit it, and then my cursor went crazy. All right. Here's some more formulas that are actually the exact same as mass percent. It's just that we have changed something at the end here. So these are formulas that are used for things like air or water quality. Parts per million is a way to express something where you have a very small amount of it in the in the solution. And parts per billion is even smaller than that. So, for example, if you wanted to express CO2 pollution, you would use parts per million. And I think like the current ppm is like 430 or something like that, which isn't great. That's how many, if you had 1 million particles of air, 430 of them would be CO2. And you might think, oh, that's not very many. We don't have anything to worry about. Let's go burn all of the paper and all the wood. And yeah, it's not great. Parts per billion, I would say things like lead in water. So like if you wanted to go and figure out how bad the water was in Flint, Michigan, you would use parts per billion. I say that with knowing a lot of people who live in Flint, Michigan. It turns out most of my World of Warcraft raid group lives there. I don't know anybody that uses parts per trillion. You could do the same thing. It'd just be times 10 to the 12. I'm sure a reason to use parts per trillion exists, but it's not common enough. So we're going to do some examples using all of these formulas on the next slide here. If you drink water from a tap, odds are it's fluorinated. And the recommended limit of fluoride in drinking water is 4 parts per million. So in order to give water the proper amount of fluorine, or fluoride ion, I should say. Fluorine is actually very toxic. Parts per trillion is how effective your tax dollars are used. That's correct. That is, I might have to remember that one. So fluoride, what fluoride does is it is a very strong bond there is a very strong bond between fluoride and calcium. And calcium is something that's very common in your body, for example, your bones. One particular thing that we like to bond fluoride to is your teeth, which is why fluoride is in toothpaste. And the reason for that, and this is just an aside in case you were curious, is that this is the formula for tooth enamel. It's something like this. Actually, I might have I don't know about this number, but what I do know about is that this is the part of your tooth enamel. If you consume stuff that is acidic, then this reacts with it and it goes away, and your teeth decompose. So, for example, if you vomit up stomach acid, which is very concentrated acid, you can get tooth decay. This is actually something that you observe in people who have bulimia, where they vomit a lot. One of the side effects or observations that you can make is that they have severe tooth decay. If you do that childhood experiment where you put like a tooth in 7-Up or Pepsi or whatever, it will decay because the acid in the soda reacts with the hydroxyapatite, or the OH part. So what we do is we try and replace it with a different ion. And the ion that actually makes a really strong bond is this one. So if you replace the hydroxide with fluoride, it is more acid resistant than the hydroxide part. And so you actually get stronger tooth enamel. So in this way, we have actually one-upped nature. So brushing your teeth with fluoride and drinking fluorinated water is actually a good way to strengthen your teeth. That said, the fluoride is so good at bonding with calcium that if you have too much of it, it can be deadly because it will bond with the calcium in your heart valves, and then your heart will stop. Because it has made a solid, basically. And that's obviously not good. So there is a limit on fluoride that is set well below that will happen, or the level at which that will happen. And here's that limit, 4 parts per million. Tripping over my tongue today. 4 parts per million. So the question I have for you is, how much fluoride in milligrams is found in a glass of drinking water? Assuming it's like about 240 milliliters. Here's the density of most water that you'll work with to 2 sig figs. So let's try this and see if we can figure this out. Boop, boop. All right. And is my problem captured? It is. Okay. So I know that the ppm of fluoride, which is the mass of fluoride over mass of the solution, times 1,000,000 I don't know why I wrote 4. I meant to write F. I thought of 4-eyed, I guess. Yeah, what is a good unit for this? You can use whatever unit you want. I wouldn't use the grams one, personally. Milligrams or micrograms would be good. So I know this information is all true because that's what the problem told me. And I need to figure out this number right here. So what that means is that I need to also figure out this number, and then this is a constant. Oh yeah, if my problem says milligrams, do that. Have you guys figured out that I don't read my own problems? So what I'm going to do is I'm actually going to set up the algebra first. So I'm going to take this, and I'm going to move it to the other side. And so that's going to look like this. So this actually has ppm on here. That's my unit right here. So this is going to go here. This is going to go here. And those are going to cancel out. So I've divided that by both sides. And so now I have mass of fluoride over mass of solution. So if I multiply both sides by the mass of the solution, that will give me the mass of fluoride in some unit. And that some unit is going to be whatever the units are of the mass of the solution. So let's figure out what the mass of the solution is. I have 240 milliliters of water, which is my solution. And I know its density to be 1 gram per milliliter. So I have 240 grams of solution. The solution being my drinking water. So now I can say, okay, well I have 4 over a million times 240 grams of water. And so that's going to be a really, really tiny number. 4 times 240 over a million. And so since my answer is in grams here, this is the number that my calculator said. 9.6 times 10 to the minus 4. And if I want to turn that into milligrams, I can do that trivially enough. And that would be the mass of fluoride. So in a glass of water, you have about 1 milligram of fluoride. And if you have more than that, then it has exceeded the EPA limit. Fluoride. Clicking all over the place. I gotta go to the right spot. There we go. All right. So now that you've seen a bunch of these examples, what I want you to do is try and do these two environmentally related problems. So if you go into atmospheric science, you're going to be studying CO2 and the effects on the atmosphere a lot, because that is a current, I would go so far as to call it a crisis, personally. When I wrote this slide in 2019, it was 410.9 ppm. What I want you to do is tell me how many milligrams of CO2 are in a human breath, which is about 6 liters. And there's the density of air. And then I want you to tell me how much lead is in our drinking water. Or actually, I give you the amount of lead that's in there. So if there are 4.5 micrograms of lead in 300 milliliters of water, and that is the limit of the amount of lead that can be in there, tell me what that is in ppb. Okay, so do these two problems. Be careful with your units, because that's where people are going to get lost on this. Is the math isn't difficult. It's just, what number do I put where? Okay, give it a shot, and I will come back in about 5 minutes or so. Type in your answers in the chat when you get them, and good luck. We're all counting on you. Oops. I muted myself before I want to talk about this. So this on the screen here, which is covering the problem right now, this is the current graph of CO2 in the atmosphere. You are here at this end, which is about 416 or 417. That is, let's see here. This is daily CO2. Here it is monthly over the last year. And you can see that there's this little sinusoidal effect. Here where we were last year, we're actually much higher than that this year. And it's going to keep on going up. So this is CO2.Earth. And it's an interesting resource if you like thinking about the end of the world, because we're all going to suffocate eventually. That's great. Let's go over the answers to these problems while there's still time. Alright, so let's write down what we know. I know that the parts per million of CO2 for the problem was 410.9 ppm. Oh, I didn't capture all the problem. It just kind of looked like I did. There we go. Let me make that a little smaller. Hopefully that's still readable on your screen. I just moved my thing here. Hold on. And I also know that I have a 6-liter breath. So that's my volume of air. And that the density of air is 1.225 grams per liter. All right, so that's all my knowns. What I want to find is the mass of CO2 in the breath. So if I write out the ppm formula, so something in ppm is equal to the mass of whatever we're looking for divided by the mass of the whole thing times 1,000,000 parts per million. So what we want to do is we want to solve for this top part, because that's going to be the mass of CO2 that we want to look at. This down here is going to be the mass of air in the breath. And then this is just a conversion factor, so you could treat it as a constant. And I know that for the formula with CO2, all of this is going to equal 410.9. So I could put that in there at the end. So first of all, let's try and figure out the mass of the total air is. And so I would do that by taking the volume of the air that I have. I'm going to turn that into a mass, and I have the density of air right there on the problem, 1.225 grams of air per liter. So that means that a 6-liter sample of air, I would have 7.35 grams. That should be a 0 of air. So that's my mass of air. That goes right here in the mass total. I now know everything that I need to get to CO2. So what was my number? 410.9 here. So we'll say 410.9 ppm CO2 is going to equal the mass of the air. Not mass of the air, I'm sorry, that's wrong. mass of the CO2 over the mass of the air times 1 million ppm. I'm just reproducing this formula. I'm just shortening it a little bit. So now this is a number that I know. It's right here. I know this number because it's a constant. I can do the division and just move everything around. So I could say 410.9 ppm divided by this 10 to the 6 ppm. And they're both ppm, so they cancel out. Times this mass of air should be the mass of CO2. And so that will be 410.9 divided by 1,000,000 times the 7.35 0 grams of air that I had. And I got 0.003020 grams. Which then means that if I'm going to turn this into milligrams, I think we can all do the conversion from grams to milligrams by now. All right, so that's the ppm of CO2 in the air converted to milligrams. So if you take a 6-liter breath and you exhale, what you didn't produce would be 3.020 milligrams. Does the density of air change as the ppm of CO2 changes? It does. And the reason for that is because CO2 is heavier than other things in the air. So, for example, O2 is 32 grams per mole. CO2 is 44, but they're both about the same size. CO2 is a little bigger. So as you get more CO2, the density will change, but you need a lot of it to change the density appreciably. And by a lot, what I mean is like you would probably need hundreds of thousands of parts per million. All right, that was the first problem. Unfortunately, that was my entire canvas, so I have to actually clear. Oops. Could not be edited. What did I do? I ruined everything. Hold on. Delete. Oh, did I make a group on accident? Yeah, I did. Get this out of here. Boop. Sorry, hold on. There we go. Okay. I hit some weird button combination that made a new strange layer on my thing here. All right, let's do this one. And hopefully I can make it a little bigger because this is hard for me to see on the screen. There we go. All right, the EPA limit for lead is expressed as this quantity. Determine the limit if 300 milliliter glass of water contains 4.5 micrograms of lead. Here's the density of water, even with the lead inside it. There's so little lead in this water that it's hard for it to affect the density in any meaningful way, even though lead is super dense. So I know that something in parts per billion is the mass of that something. We're going to say lead. And it's a billion, so it's 10 to the 9 ppb. So in order to find this limit, because this time I don't know this number, I want to actually calculate it. So I need to know this, and I need to know that. Now I do know the mass of lead, so that's actually most of the way done. What I need to do, though, is get the mass of the lead and the mass total to be in the same unit. So let's work with the mass total to start here, because It's in the obnoxious unit right now, which is milliliters. So I know that I have 300 milliliters of water, and I know its density. So I can make it a mass, and that is 1.0 grams per milliliter. You might be looking at that and saying, well, why the heck did you write it like that? Well, I lost a sig fig when I multiplied by 1.0, so now I only have 2 sig figs. Now, I don't really want to have this number in grams because my mass of lead is in micrograms. So I'm actually going to turn this grams into micrograms. Because in a microgram, there are 10 to the minus 6 grams. And when I do that, I get... Should be 3 times 10 to the 8. I don't know why I'm playing with my calculator to get it to say that. There we go. So that's the mass total of the solution. Is 3 times 10 to the 8 micrograms. The amount of lead I had in there is 4.5. So I feel pretty safe that saying that this mass is going to be kind of small. So the parts per billion of the solution would be 4.5 micrograms over 3.0 times 10 to the 8 micrograms, which is the mass of the water, times 10 to the 9 parts per billion. And I got... My calculator would stop putting in the wrong mode. Looks like I got 15. It looks like other people got 15 also, so that's good. All right, you are now all qualified to be water treatment experts. And having been somebody who has done water treatment stuff as an undergraduate for just like a research thing that they were doing, they needed volunteers. So I got up at like, I went to the lab at 8 p.m. and then we left at 6 a.m. because in college you can stay up all night, like all the time. I actually thought that the water treatment experiments were kind of cool. I just did physical analysis, like prepping them. Other people got to go out to like the this was in Irvine. They went out to the ocean and collected the water, and they would do this all night. And then when we were done with our sample preparations, like measuring pH, measuring turbidity, putting them into the bacterial growth solution to see like what was actually in them, then we just got to hang out, and we were paid like $20 an hour as undergrads in 2003, which was a lot back then to a college student. So water treatment is pretty awesome, I have to say. I think that that's chapter 6. Yeah, it is, because we're not going to do the balancing equations part. So what I'm going to do, let me put this back on the screen real quick. I'm going to put this on the screen. We're going to skip past all this because we're not actually going to do balancing equations in this class. But you're free to look at these if you would like to. I feel like balancing equations is pretty trivial, but it's very important for 162, and it's always reviewed. So we're not going to focus on it in this class because it's just another thing that takes up time. Instead, let me get to the summary here, where we can talk about what we did in Chapter 6, because Chapter 6 was short, but it's actually very important. So in Chapter 6, we covered empirical formulas and how to determine the ratios between different elements. And once we figured out those ratios, how to represent those as a compound formula. And then finally, using mass spec, how to put all of that information to good use to make an actual formula here. Then finally we went to molarity. Not finally, I'm sorry. Then next we went to molarity. Molarity is a way to express concentration. We learned how to do that by using solutes and solvents. And we then described how to prepare solutions using various reagents, either by like adding a solid to a container and putting water in it, or putting a liquid in and then adding water to that, and how to use volumetric glassware. And then there's what we just did today, which was how to express solution concentrations in different units and do those calculations. Again, you don't need to worry about this, because we're not going to do it in this class. All right, so that's going to lead us to, first of all, the break. So let me put up the title card real quick. Wait a second. We're about to do quantum mechanics. Let me put up the correct title card, because, as I mentioned before, this is where the class starts to get very difficult. I like to call it the dark hour of Chemistry 161. So I went and got some nighttime pictures to show the campus off when it's a little bit more gloomy. I'll still put the timer on the board. And I don't have the timer actually on screen here. Oops, that was me playing Zelda Randomizer last night. So we're going to take a 10-minute break, and when you come back, be ready, because quantum mechanics is one of the craziest, most difficult things you will probably conquer in chemistry. And I actually have music for that, so I will turn that on, and I will see you in a bit. I know I tried. All right, so let me push this button right here. There we go. All right, so it did capture the right window. I forgot that I didn't tell it to do this, so it sort of like jumped in there. This is chapter 3. Chapter 3 is probably entirely new. If you have taken Chem 140, it's very unlikely that you have done much except for maybe a little discussion on electron config, depending on what instructor you had. But most of this is going to be completely new. And what that means is we're going to try and go a little bit slower than normal because we're out of the review stuff. But also that the amount of detail that we're going to have to pay attention to is much, much higher because all of this is going to basically be important. And this chapter is really long. Let me look at how many slides are in chapter 3. The last chapter had like 60 or 70 slides. This one has 155. We're going to be in chapter 3 forever, basically. And then when we're done with chapter 3, we can finally go back from the dark hour to the happy, fun times of whatever. But nope, not for now. There we go. So we're going to be here for a while. There is a light at the end of the tunnel, and it's called light. What is light? Well, let's talk about it. Light is a very complex thing, and in order to analyze it, we need to understand its properties. So the first thing that we want to understand about light is that it is a form of electromagnetic radiation that travels with oscillating components. And what that means is that when something oscillates, it has a maximum and a minimum, and it goes up and down, and up and down, and up and down. Those maximums and minimums that we observe can be measured, and we're going to talk about what that means in just a little bit. But what's important to note is that because it has these wave-like properties... Oops, sorry, that was a really terrible straight line. Because it has these wave-like properties, we can measure them. Now, there is another property of light that can be measured, and it is that it has energy. Now, energy for light is measured in something called a photon, and it turns out that photons are discrete. And so these two things seem a little bit counterintuitive. You might think of something that is a wave as like, oh, that's a continuum. I can have any energy I want between the maximum and the minimum. But the fact that light can be discrete and exist as something called a photon means that it doesn't do that. So we care about these photons because they contain energy. But we also compare the wave nature of light to that and go, wait a second, that seems impossible. And to someone studying classical physics, that is impossible. And so we call this the wave-particle duality of light. So right off the bat, slide number 1, light doesn't make sense. And what I'm going to try and do is I'm going to try and explain why that is by drawing a picture. Oops, I don't want Control Delete. I want Control All. There we go. All right, so the first thing we want to do is we want to draw light as a wave. Something like that. And if I were to say, I want something to be this energy, well then here you go, it's right here. But if light is a particle and has a discrete energy, then that means that there is some quantity of energy in each particle. And we would call that quantized. So what that means is that if I have this much energy in a packet of light, then I would actually have something that looks more like this. for my wave. And so on and so forth. Now, if I were to say I want this much energy, how many light packets do I need to get exactly that amount of energy? I would say impossible, because I'm not on a platform where that energy is. And so light does have these discrete quanta, and so you can't get an exact amount of energy. But it also behaves like a wave, where it sure looks like you can. How the heck does light exhibit both properties at once? And the answer might surprise you. And we're going to talk about this a lot later on when we get to the Schrodinger equation and the not Schrodinger equation, sorry. Schrodinger's cat, the Heisenberg uncertainty principle, and why all of this is called quantum mechanics. Quantum mechanics, and you're only really going to hear this here from me, so quantum mechanics, I guess I wrote. Quantum mechanics is really a secret code. And that secret code is really, really small stuff. That's too many L's, rats. Does crazy shit. That's really all quantum mechanics is because everything is so tiny, it doesn't behave like we would expect it to. And so the consequences of the wave and the consequences of the particle nature of matter start to blur together when you get stuff that is so tiny that we can't resolve it. Okay? So the theme of chapter 3 is, well, it's this. It's crazy shit. And so we're going to study that crazy shit here. Now, in order to understand this, we're going to try and take it slow, like I said before, but 2, we got to throw a lot of different pieces at you, and all I really am expecting you to do is catch them and then put them on the table and then know that they're there. We're not going to really assemble the pieces for just a little bit. In fact, we're not going to be able to get all those pieces down on the table today. But we're going to talk a little bit about light, and then we're going to talk a little bit about how waves work, and then we're going to talk a little bit about particles work, and then hopefully from there we'll be able to build a picture. So let's do that. So we're going to start with waves. The only thing that we really need to know about particles is that, yeah, particles exist, so like an electron is a particle, but light can behave like a, quote, particle. And so we'll treat it like that later on. If you have taken a basic physics class, so like in high school, when I took physics, we did a bunch of stuff with light, and we talked about waves and stuff. You may have seen some properties of light, such as like its velocity, its amplitude, its frequency, etc., stuff like that. How fast is light? Light is stupidly fast. Like, I can't even remember the Spaceballs reference. It's as fast as plaid, right? They've gone to plaid, ludicrous speed. We represent the speed of light by a constant, and this constant represents the speed that light will travel in a vacuum. Now, if there's stuff in the way, you could probably hear I almost said a different word there. If there's stuff in the way, light will slow down slightly. For instance, light will travel slightly slower through air than it will through the vacuum of space. But to 3 significant figures, this number is good enough for our purposes. 3 times 10 to the 8 meters per second. Now, a consequence of this is that light goes so quickly we could treat it as, over terrestrial distances, more or less instantly. So if you have something like a storm, where you have a lightning flash, the light will hit your eye from the lightning strike instantly. But the sound will travel much slower. The sound travels at about 300 or so meters per second. And so what that means is that if you treat the lightning flashes the instant the lightning impacted, and then you count seconds off, you can figure out how far away the lightning strike was from you. Every 3 seconds is about 1 kilometer. The reason for that delay is entirely due to the difference in how fast light travels and how fast sound travels. Both of them are waves, but light just happens to travel that much more quickly. Now, this number is going to be something that we use quite a bit, because we're going to be using light for our experiments to determine the nature of the atom, because light, it turns out, is something that atoms give off. If you've ever gone to like Las Vegas or anywhere at night or played Shadowrun or Cyberpunk or anything, you see neon tubes everywhere. It's all neon. It's all blue and pink and orange and gray. And all of that comes from excited atoms. Atoms emit light when you excite them. And what that means is if atoms emit light, we can use light back on the atoms to get information. So understanding properties of light, like its speed and its amplitude and stuff, is going to be critical. And we'll need this number to do that. Thunder is the sound that you hear. Lightning is the flash of light and the electrical conduct that occurs between the cloud and the ground. Just in case you didn't know that. Like any wave, light exhibits wave properties. And so we can measure those properties if we analyze them. So for instance, the first trait that we're going to look at is called the wavelength. The wavelength of light is the distance from any two identical parts of the wave. And so I can list a bunch of them here. So I could say where it's descending through the midpoint, or I could even pick the valley down here. Any two that I pick are going to be the same distance apart. Isn't neon just red? It's kind of reddish-orange, but yeah. In fact, later on, I'm going to make you calculate the color of different gases. And you'll be able to do it using what we're going to learn today and on Tuesday. Actually, when I say different gases, I actually mean hydrogen, because the other examples are a little too complex. But you will be able to calculate, using math, what color hydrogen gas is when you turn it on. Now, the amount of energy we have for the peak and the crest of the wave is called the amplitude. And so that's in purple here. I could do the same thing. I could go all the way down to this end. Both of those are the amplitude. Now, depending on what you are looking at, the units for amplitude will change. For light, it doesn't really make sense to measure the height of a light wave. Like, that's not a thing that we can really measure. We can measure its wavelength based on its energy, but we can't really measure its amplitude in terms of, like, how tall the wave is. Instead, we could say, like, how much energy the wave has, or how many different waves there are. So you could use amplitude as a number of, oh, this is how many different photons I have. And as you add them together, the wave gets bigger. And we'll show how that works later on when we talk about wave addition and subtraction. Now, both of these affect the amount of energy that the wave has. And so we're going to consider both of them, but we're going to mostly focus on the wavelength. This is the more important of the two. Now, the next property that we can examine is called frequency. And frequency has some things to note. The first of all that I want to note is that this is not the letter V. This is the Greek letter nu. Okay? So if you type in the symbol font and you push the letter N, it'll spit out something that looks like a curly V. This is going to be obnoxious later on, because we're going to have a formula that uses V for velocity, but all of the formulas we're going to use up until that point use nu, which is frequency. I write my nu as just really curly to try and differentiate it from V, which is pointy. You can see that there is a slight font difference, because here is an actual V and then this is nu, but it's not very obvious, so just be very careful. When you are looking at formulas, they will write nu when they intend it to be nu, and they'll write V when they intend it to be V, and depending on the font that's used, it might look very similar. Now, frequency is related to wavelength. So if I have a region of time, and we'll say that this length of time is 1 second or whatever, and my wave goes like this, do 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 do, in 1 second. So it did 1 wave, 2 waves. It did 2 waves in 1 second. Whereas this one down here in the purple would do 1, 2, 3, 4 waves a second. And then this one down here does 1, 2, 3, 4, 5 waves a second. Now, you can kind of figure out where this is going and which of these has more energy to it. For instance, if you stood up from where you were sitting right now and you jumped at a speed of 1 jump per second. Okay, now that you're done jumping, I guess, I don't know. So 1 jump a second, so you jump, jump, jump. Now try and do 5 jumps a second. Jump, 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 jump. One of those is going to be way harder to do, right? In fact, one of them might be impossible. It takes way more energy. So the higher the frequency, the higher the energy. And the unit that we use for frequency is called the hertz. Now, this isn't the hertz that you rent cars from. This is hertz as in per second. So the units of hertz are just per second. So this that I'm highlighting right here is the hertz. Now, to represent that, we actually have this notation here. We would write the exponent as negative, meaning that it goes on the bottom of a fraction. Now, if I take how many waves I have for this photon, and I multiply that by its wavelength, then what I end up getting is a speed. Because if I have something that moves, or it has a wavelength of some length, and I times it by something that has some frequency, I get a velocity. So, from this information, if I take lambda, which is the wavelength, and I multiply it by nu, which is its frequency, and I got a velocity, what velocity might that be for light? Well, there's only one velocity we've talked about so far. And so it turns out that the speed of light is simply the product of its wavelength and its frequency. So that formula is going to be very useful to us too, because the speed of light is something we can easily measure. And we can determine wavelength by using various means, such as like a prism or something. You can diffract light based on its wavelength by shooting it through a prism or a diffraction grating or something like that. Or you can determine its frequency based on its energy. There's a bunch of ways that we can measure stuff. And we're going to show a bunch of them in this class. So when we look at how we can consider the energy of light, we've already talked about frequency here. And I don't have a vertical highlighter, so I got to do it this way. As frequency increases, the energy of the photon also increases. But if we look at amplitude, increasing amplitude also increases energy. And so what that means is that if I have multiple waves with the same phases, then a higher amplitude wave is just more photons. And so if I have more photons, I therefore have more energy. And we've already talked about frequency on the previous slide and just now. So the more times that you pass through the center line over a unit of time, the higher energy the photon must have. And you can think of that as like the jumping example. You could think of that as if you had like a rope and someone was holding the other end and you tried to swing it around 1 time a second, like a jump rope, and then you tried to do it 20 times a second. It's way harder to do the second one. And all waves behave like this. So that's convenient that light behaves like this too, because we can take very simple examples and learn from it. Now, what light can we perceive? There's all sorts of light out there. In fact, some of it's hitting you right now. This poor woman being attacked by a rainbow. And the light will hit random surfaces and substances, and things will happen to it. And so we need to understand what we are observing to understand what's going on. So the first thing we want to talk about is that we can only see certain colors of light. And those colors are shown right here with this prism. White light, when shot through a prism, will expand into all of its different colors, and actually more than that. Other stuff that's in white light, we won't be able to see. We can only see the two extremes. We can see up to red and all the way down to purple. Now, what feature of light dictates what color it is? It turns out that that feature is how much energy it has, which is related to the frequency, which is related to the wavelength. So, wavelength, oops, I hit control, hold on. Wavelength is a really practical way of describing what color light, why isn't it working? There we go. What color we have. So the wavelength determines the color. Now, white light has all the wavelengths mixed together because it's just a jumbled assortment of photons. Splitting them apart is what creates the different colors that you can see when you have a prism. Now, when light strikes objects, some of those wavelengths are absorbed by the material. Some of those wavelengths are reflected by the material, or they're emitted because after they're absorbed, the energy that's available emits in that color. When light bounces off something, that light can then go to your eye. Oops, it's supposed to be an eye. There we go. And when that light hits your eye, you see it. The light interacts with retinol, which is a substance that is in your eye. It flips a molecule, and then that sensor goes to the brain, which your brain interprets as, oh, that's red. So you can visually interpret certain wavelengths of light, and our brain has processed those as color. For example, I'm looking at the window, and I see a bush, and the bush has light reflecting off of it. That light came from the sun, it hit the leaves, bounced off of it. Only a certain color bounced off of it. The other colors were absorbed. And then that light from the leaf reached my eye, and my brain processed that as green. And that all happens in a very short amount of time, because light is very fast. If you turn off the light, like, I'll just go out and turn off the sun right now. No, I'm just kidding. If you turn out the light in your room, all the color goes away, because no light is hitting your eyes. Now, that leads to a very interesting philosophical discussion. What color is something when the lights are out? And the answer is, well, it doesn't have a color. Like, my red t-shirt isn't red if there's no light hitting it, right? Because what is light? It's what light is hitting surfaces of substances. Definitions are scary. Now, obviously, that seems like a very weird thing to say. My red t-shirt isn't suddenly not red when I throw it in the washing machine and the light is closed in there. It has those properties. So, it's important to note that these definitions might be a little bit weird when we start talking about stuff at a very technical level. So, light is one of those things. Light is a very specific substance that we're going to have to define very carefully. Now, what parts of the spectrum do you see? If I were to plot the wavelengths that you could observe, the minimum wavelength that you observe is 400 nanometers or so, and that's purple. The maximum that you can observe is 700 nanometers, which is red, and you can get all the colors in between that. Now, depending on your visual acuity, you might be able to go slightly higher or lower than this range. But most normal human vision is in this region. And in fact, some people who have color blindness won't be able to see some of the extremes in this or some of the parts in the middle. And that has to do with certain structures, rods and cones in your eyes. The rods are for intensity of light, cones are for color, that are sensitive or lack sensitivity to certain wavelengths. And so if photons of those regions hit your eyes, you just don't pick them up. Now, other wavelengths that are beyond these regions are invisible to the human eye. We can interact with them, but we can't use our eyes to do it. What we have to use is mechanical sensors. For instance, heat and infrared radiation is a form of light, and we can sense that with things like our hands. So you could feel if something is hot just by putting your hand near it. So you can sense the infrared radiation that's coming from it. You don't get much information because touch is not as finely resolved of a sense as vision is, but it does allow you to get some information. If we use a mechanical sensor, you could get a lot more information about light because it can detect different wavelengths based on molecular vibration or stuff like that. Other devices use electrons to detect light and its influence and how it interacts with them. Oops. And that's actually the important part here. I tapped the paper on accident. So this is actually the key thing here, is that, hey, if electrons interact with light, we're going to be able to do something with this. And that's going to be useful to us. So here's the infrared spectrum. Not the infrared spectrum. Here's the electromagnetic spectrum, of which infrared is a small part of it. This teeny tiny chunk in the middle right here is the part you get to see with your eyes. Light expands in both directions much further than the visible spectrum. And so let me get a different color highlighter out here. We'll do red because this is the more dangerous side. So everything on the left here, these are energy levels that are much more intense than your eye can handle. In fact, they are much more intense than most things can handle. So after purple, or violet, I should say, we have the ultraviolet region, which is dangerous to humans. If you go outside without sunscreen, the UV radiation from the sun will give you a sunburn. What's actually happening is that the sun is emitting light that is so high in energy that when it hits your skin, specifically places that have double bonds in your skin, it excites them to the point where they break. And breaking bonds in molecules, particularly in your cells, is not good. In fact, this is how cancer arrives, is you get cancer from random destruction of bonds in your molecules. And if those bonds are destroyed, the molecule might denature and form a different bond, which could then be malignant, is the word I want. And as you increase the energy of these photons, this possibility becomes more and more destructive. So you may have heard stories about how people, when X-rays were discovered, this was actually a really dangerous technology because people just X-ray themselves all the time. One story that I can think of is that if you went to a store where you buy shoes, nowadays when you put on shoes, you just put your feet in and you kind of wiggle your feet and you're like, okay, yeah, that feels good. But back when X-rays were discovered, they had this X-ray booth and you could put your foot in the shoe in the X-ray booth and you could see your toes and your bones inside the shoe and how it fit. And people are like, yeah, this is super cool. And it turns out that all the people that demonstrated that, so all the people that were working at these shoe shops, ended up getting cancer in their skin, in their bones, in their feet, because they were demoing it so often and exposing themselves to X-ray radiation. There's all sorts of really bogus stories, not bogus, I should say, just terrible stories about radiation out there. And these are some of them with X-rays, because X-rays were a really common thing when they were discovered. So we used them everywhere, and then we realized, oh, that's not good. Cosmic rays are the things that come out of, say, black holes colliding, very high energy solar events such as a supernova. Not solar as in our sun, sorry, star events. Our sun hopefully will not supernova for a while. But if it did, you'd see a lot of cosmic rays before it all ended. Oops, I didn't mean to go back. On the other side of the visible spectrum is stuff that's relatively harmless to you. Infrared light is something that all substances emit. For example, you are emitting infrared radiation right now. That is just heat, which can be detected in a specific tool that detects infrared, such as night vision goggles or thermal sensors. So like those thermometers that you point at things and they tell you what temperature they are, those absorb infrared light and can detect it. If you have a wireless controller or a remote controller that you use for your Xbox or your PS4, those use infrared light to communicate with the device, which is why the response on them is really good, because you aren't actually limited by the distance from your controller to the console. You're limited by how fast the electric components inside those can process your signal. And it turns out that that's pretty fast, so there's not that much lag when you're playing a wireless controlled game, which makes them practical. Going down the wavelength scale, we have terahertz and microwave. This is the region in which things like your cell phone, radar to determine the weather, and then your broadband connection through your router. Those tools will use light that is at a low frequency. That frequency is low enough energy that it doesn't really interact with things like walls. So you can broadcast your cell phone through a wall. You can have a router, and that signal can go through walls. It's limited, but it can. And then as you go down lower to that, so microwave would be like your microwave oven. Your microwave emits light to cook things. And then finally we have radio, which is down at the very end of the spectrum, which is the lowest energy of all. Now we're almost out of time, and this is actually where we're going to call things for the day, but I do want to point out one thing really quickly. So this specifically right here, a while ago, and this is a sort of like, I don't want to call it a meme because it was more of just like a hoax, I would say. A lot of people thought that using cell phones, when cell phones started to proliferate in like the late 90s and the early 2000s, I would say, a lot of people said, oh my goodness, don't use cell phones, they cause cancer. And that is a thing that, by looking at the scale, you should immediately be able to see that that's gotta be bullshit. And the reason for that is because cell phone radiation is around in this region right here. But if cell phone radiation, and I say radiation as in light, if the light that was emitted from your cell phone could ionize you and cause damage, and this actually does go into the 5G discussion too, because 5G is the same thing, it's cell phone radiation. Could these be causing cancer or coronavirus or something stupid? And the answer is, well, if anything in this region did that, then everything above it would do that too. Which means that not only would your remote control, you point it at your little brother and give him cancer, but everything that emitted a color would be carcinogenic. I hope you're not wearing green, because that causes cancer. But you know what causes cancer more than green? Blue. And purple. Oh my goodness. Only royalty can wear purple, because they get to give cancer to everyone. How stupid does that all sound? Yeah, it's dumb, right? So, we know that visible light doesn't cause cancer. And we also know that things like the remote control, or your Xbox controller, or your PlayStation 4 controller, or whatever, don't give you cancer, because there's no way we could sell those to you if everybody died. How would you buy more games if you just died, right? Green is poisonous for other reasons. I like green. It's the color of orcs, which are like my favorite creatures, so. But, oops, I didn't mean to go to the next page. But what's important to note here is that we have to be really critical of all of these meme sorts of things that are out there. Because a lot of these are going to be based on, not science, but just like somebody saying something and then people latching onto it. It's very human to believe people, even if what they are saying is bullshit. And so what we're going to try and do in this class, and all the classes that you do take, is provide you with data and things that we have tried and observed. And then you have to make your own conclusion, really. Okay? So the conclusion that I draw here is that, one, cell phones and 5G do not cause problems in terms of like radiation hitting you. So yeah, if you see a bunch of people that are like, oh yeah, 5G, it's going to cause cancer for everybody, tell them like, no. If that caused cancer, then so would the router in your remote. In fact, most people that I would say who would make that argument probably have like an old TV remote. You should just take that remote and point it at them and just hit the button and say, I'm just hitting you with a photon that has higher energy than 5G routers. So, enjoy the cancer. Don't actually do that. I'm not going to advocate that you give your parents cancer. But I mean, just to prove how stupid that sounds, like, that could be a good thought experiment. Because you're not going to hurt anybody by pointing the remote at them. And you're sure as hell not going to hurt anybody by being exposed to 5G wireless data. Because it's in the same frequency range as all these other things that don't hurt us. Alright, thanks for coming to my TED Talk. That's all we're going to do for today. I'm going to put the title card up. On Tuesday, we will continue with Chapter 3. Obviously, we are going to be here a while. What slide are we on? Yeah, I got to slide 10 out of 155, but I only had an hour, so that's fine. We're going to do some math problems with light, and then we're going to get to the Bohr model, which is going to be the last thing that we do with the calculator in this class. After that point, we do not need a calculator anymore. It's all conceptual. So be ready for that. Do keep in mind that the midterm is on Monday of week 6. There will be a little bit of stuff from Chapter 3 on the midterm, but not very much. I mostly want to just test you on Chapters 1, 2, and 6 because I kind of want to have the math midterm and then the second midterm be the not math midterm. I feel like that is a really good divide for the class. So that's what's coming up. If you have any questions over the weekend, please let me know. Send me an email. Use the discussion. Anything you post on Discord that you want me to see, you got to get it to me somehow because I'm not in that Discord. So just keep that in mind. Thanks for watching. Have a wonderful weekend. And enjoy the sun, at least the part of the sun that won't hurt you, which is this part right here. Thanks for watching.